Hello to all, welcome to the channel Money's Gate Tech Vision. In this lecture, I am going to solve GATE 2026 problems for the topic Control Systems from the discipline EC. The topics which I have taken is common for all the branches, common for electrical, electronics and instrumentation. So those branch candidates can watch this video. Let me start solving the problem. The first problem, this is taken from the topic Routh Array's criterion. Consider the unity negative feedback control system shown in figure. The value of gain k greater than 0 at which the system will remain marginally stable is. Okay, the stability condition is given. We need to find the open loop gain k. Okay, so let me use the Routh Array's criterion. First we find the characteristic polynomial. So we know for a closed loop system 1 plus g of s h of s equal to 0 is a characteristic polynomial. So let me find the characteristic polynomial. Here h of s equal to 1. So g of s is given as k by s plus 7, s plus 11. Okay. So this is simplified as s square plus 7s into s plus 11 plus k equal to 0. So we find the polynomial s cube plus 7s square plus 11s square plus 77s plus k equal to 0. So s cube plus 18s square plus 77s plus k equal to 0. So we can use the Routh Array's criterion to find the limit of stability. So from that we can find the open loop gain. Okay. So let me use the Routh Array's criterion. So s cube coefficient is 1, alternate coefficient is 77, and then s square coefficient is 18 and k is the constant. And then to fill the s power 1 row by the Routh array formulation 18 into 77 minus k by 18. Okay, and s power 0 is k. So for the stable system, the first column of the Routh array should be positive. So from that k should be greater than 0 and this term it should be greater than 0. So simplifying that 18 into 77 minus k should be greater than 0. That means k less than 18 into 77 which is 1386 for the system to be stable. But here in this problem marginally stable condition is given. So after this limit if k reaches 1386 it will remain marginally stable. The system will remain marginally stable. Okay. So if k greater than 1386 means the system will become unstable condition. So marginally stable means the roots will lie on the imaginary axis. That is the mean. Neither in the left half of S-plane nor in the right half of S-plane. Okay. So thus we can find the open loop gain by using Routh array. So another one thing, since this is a cubic polynomial, we can find directly by equating the internal product of coefficients and external product of coefficients. So k into 1 external product which is equal to 18 into 77. So therefore k equal to 1386. So by this method also we can find for the cubic polynomial. So if other than those polynomial, if it is higher order polynomial means we need to use Routh array and we can find the k. We can find the k. Let me move to the next problem. This problem is taken from the topic transfer function of the system. Feedback and transfer function of the system. A control system is shown in figure. Which option represents the correct transfer function of the system? Now observe the block diagram clearly. Here we are having two summing points. Summing points can be called as adder or it can be called as comparator. Okay. Two summing points which are in connection, which are in signal flow connection. And here in the output side we are having one summing point and in the input side we are having another summing point. Okay. So now summing point and summing point, there is a signal flow. From the output summing point and to the input summing point, there is a signal flow connection. So for this block diagram reduction technique, it's somewhat toughest. So for those type of block diagram, we cannot choose block diagram reduction method. So I'm going to use the signal flow graph reduction method to find the transfer function. So let me convert this block diagram into signal flow graph now. So first input, I'm going to take this as first node. And then the summing point, I'm going to take this as second node. So this summing point, first this input side summing point and takeoff point can be combined. But for accuracy, we can take it separately. Okay. Because internal connection is there, internal connection is there between the input side summing point and output side summing point. So I am going to separate this as, I am going to take this as single node. Take the summing point as single node and this takeoff point as another node, another single node, third one. And here also, I am going to take this as fourth node. And this summing point, I am going to take this as fifth node. And the output node, sixth node. Okay. So let me draw the signal flow graph now. First node, second node, third node, fourth node, and this is fifth node, and here sixth node. Okay. Let me write the signal flow. From 1 to 2, there is no block. There is no block. The gain is 1. We can represent the gain is 1. And 2 to 3, there is no block given. So we can represent that gain as 1. And from 3 to 4, two signal flows are there. One is to the summing point. Other one is to the output. Other one is to the fourth node. So third to fourth, we are having the gain 1 by s plus 4. And fourth to fifth signal flow is there. We can represent that gain as 1. And from third to fifth, so another signal flow is there. Another signal is given as input. That gain is 1 by s plus 4. Since this is a negative operator, so we can represent this signal, this gain as minus 1 by s plus 4. Okay. And then from the fifth node to second node. That means from the output side summing point to the input side summing point. Signal is flowing to the input side summing point. So for that, we can represent like this. And we can put our arrow mark here. And this is gain minus 1. Since this is a negative operator, we can represent that gain as minus 1. So this is the equivalent signal flow graph for the given block diagram. Now, using the signal flow graph, using Mason's gain formula, we can find the transfer function equal to 1 by delta summation k pk del k. Okay, where pk is the forward path gains for k number of forward paths. And where delta is, we know, 1 minus sum of individual loop gains and plus sum of two non-touching loops, and it will be further continued. Okay. Okay. So let me find the forward paths first. Forward path. It is a path, it should start at the input node and it should end at the output node. Okay. Forward path. Without the node should not return back. Forward path. The direction of signal flow, it should not return back. So here, the forward path is 1, 2, 3, 4, 6. So this is only the forward path we are having in the signal flow graph. So path gain is 1 by s plus 4. Okay. So delta 1, all the delta, we can find delta 1 afterwards. And let me find any individual loop is there. See, individual loop is, it should start at the same node and end at the same node. So if we consider second node, second to third, second to third, third to fourth, and fourth to fifth. And here it is returning back. Here it is returning back. But we cannot take this as individual loop. See here, we cannot take this as individual loop because we are having the input from 3 also. From third node and fourth node, the two signals are flowing and it is combined at the fifth node. So we cannot take this as individual loop. We cannot take this as individual loop. So we can conclude here there is no individual loop. There is no individual loop in the signal flow graph. So we can write delta equal to 1 minus 0, which is equal to 1. Okay. There is no individual loop. And then transfer function. We can find the transfer function. So 1 by delta summation pk del k. So only one forward path. So k equal to 1. So p1 del 1. So del 1 also there is no non-touching loops. There is no individual loop itself. So we can conclude delta 1 equal to 1. So here only p1 del 1 by delta. So that is p1 is 1 by s plus 4. Okay. Delta 1 is 1. Delta also 1. 1 by 1 will get cancelled. So 1 by s plus 4 is the transfer function of the given block diagram. So here, let me observe the option 1 by s plus 4 is in the option B. So option B is the correct answer. Let me move to the next problem. This problem is taken from the topic compensator, design of compensators. For the control system shown in the figure, the transfer function of a plant is given. It is connected in cascade with a compensator. Compensator function is given where k and alpha are positive real valued constants. Which of the following k alpha represent the correct values for the closed loop system to have poles? So the poles are also given. We need to find the constants. Okay. So compensator block diagram is given. So from that we can find the closed loop transfer function. So we will find the closed loop transfer function first. Y of s by R of s equal to cascading this C of s into G of s. It's the open loop transfer function plus 1 by 1 plus C of s into G of s. H of s equal to 1. So we can eliminate that equal to, by simplifying, k into s plus alpha by s plus 1 into s plus 2 by 1 plus k into s plus alpha by s plus 1 into s plus 2. Okay, simplifying this will become, I am going to take the denominator only because poles are given. Poles are given. So I am going to take denominator only. Simplifying the denominator, it will become s plus 1 into s plus 2 plus k into s plus alpha equal to 0. Okay. Now I am going to substitute. Here there are two poles, s1 equal to minus 3 plus j root 5 or minus 3 minus j root 5. Either we can use this or we can use this. So I am going to use minus 3 plus j root 5 to find the k value and alpha value. So I am going to substitute minus 3 plus j root 5 plus 1. Instead of s, I am substituting j root 5 plus 2 plus k into minus 3 plus j root 5 plus 2. Sorry, plus alpha equal to 0. Okay. Now, this is simplified as minus 2 plus j root 5 into minus 1 plus j root 5 plus k into taking real parts and imaginary parts separately. Minus 3 plus alpha is a real part plus j root 5 is the imaginary part. And simplifying this, multiplying this, it will become minus 3 j root 5. Okay. And then here minus 3 plus alpha into k is the real part and jk root pi is the imaginary part equal to 0. So we need to find k and alpha. For that, I'm moving this part to the right hand side. Okay. So minus 3 plus alpha into k plus jk root pi equal to 3 plus j3 root pi. Now equating the real parts and imaginary parts. First I am going to equate the imaginary part. So equating the imaginary parts, k root 5 equal to 3 root 5, hence k equal to 3. Hence k equal to 3. K root 5 equal to 3 root 5 means k equal to 3. So we found out k. And then by substituting k value by k value in equating the real parts. So equating now real parts. Minus 3 plus alpha into k equal to 3. Equal to 3. So 3 by 3 equal to 1. So minus 3 plus alpha equal to 1. Alpha equal to 4. Okay. So we found out k and alpha. Now see the sequence. First k, second alpha. So 3, 4 is the answer. Option B is the correct one. So thus we can find the constants. We'll move to the next problem. This problem is taken from the topic state variable analysis. State variable analysis. State and output equations are given. We need to find the transfer function of the system. Okay. So we know the state equation and output equation general form. So this is the state equation. We know ax plus bu. State equation. And y equal to output equal to cx plus d. This is the output equation. This we know. Okay. Now we need to find the transfer function. So by using this expression, we can find the transfer function directly. C into Si minus A the whole inverse into D plus, into B. This is B matrix. Into B plus D. Okay. So using this relationship, using this formulation, we can find the transfer function directly. Okay. So here A matrix is given. A equal to minus 4, minus 1.5, 4, 0. And B is 2, 0. This one. And C is 1.5, 0.625. Okay. First we need to find the Si minus A, the whole inverse. First, let me find Si minus A matrix. Si means using the identity matrix, yes, 0, 0, yes, minus the given A matrix, minus 4, minus 1.5, 4, 0. So the matrix will become S plus 4, minus 1.5, minus 4, yes. Okay. So first let me find Si minus A whole inverse. For that we need to find the determinant and adjoint. So if you find the determinant, S square plus 4x plus 6. And I'm writing here adjoint of Si minus A. So these are all input. Okay. Si minus A equal to. So adjoint by using the cofactor transpose of the cofactor matrix. Let me find the cofactor and transposing that cofactor matrix, it will become yes. 4 and here 1.5. S plus 4. In the whole inverse. Si minus A inverse adjoint by determinant. Okay. So that is 1 by S square plus 4S plus 6 into that adjoint matrix. Okay. So now we will use this relationship to find the transfer function. So transfer function equal to C matrix, that is 1.5, 0.625 into inverse, that is 1 by S square plus 4S plus 6 into what we found out, S 1.5, 4, S plus 4. S 1.5, 4, S plus 4 into the B matrix is 2, 0. Okay, this is a column matrix and this is a row matrix. So I am going to write the determinant outside. Let me multiply this matrix. 1.5, 1.5 into S. So 1.5 into S, 1.5 S plus 0.625 into 4, that is 2.5. This first row, first column. And then 1.5 into 1.5, 2.25 plus 0.625 S plus again 2.5. Okay. Into the B matrix is 2, 0. Now, multiplying this row matrix and this column matrix. So 1.5s plus 2.5 into 2. Okay, 1.5s into 2, 3s, 2.5 into 2 plus 5. Okay, so this into 0, that is 0. So 3s plus 5 in the numerator and in the denominator s square plus 4s plus 6. So this is the transfer function. This is the transfer function of the given transfer function found out from the state and output equations for a control system. So let me observe the option. In the option C, we are having that answer. So option C is the correct one. So thus we solved 4 problems which I have taken from the electronics and communication gate paper. Thank you very much for watching the video. This is the channel Mani's Gate Tech Vision. This is the channel for engineering lectures. You can subscribe my channel. You can view. If any queries, you can ask me. You can mail me. My mail ID is dmoneylecture@gmail.com. Thank you very much.